Hello, and welcome to Sleepy Lab. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you're simply someone who likes to drift off to thoughts deeper than dreams, quieter than silence. Either way, you're exactly where you need to be. There's nothing you need to do right now, no list to remember, no decisions to make. Just let your breathing slow, let your shoulders drop, and allow your mind to settle like dust in still water. Tonight, we're going somewhere most humans will never go. Not into space, but into the opposite direction. Down. Far down. Past the reach of sunlight, past the warmth of the surface, into the deep ocean, where pressure replaces light and stillness becomes a kind of language. This is a place that covers more than half of our planet, and yet we know less about it than we do about the surface of the moon. It is vast, cold, and strangely alive. And tonight, you'll hear about its soft mysteries, the creatures that glow without fire, the mountains no one has named, the snow that falls upward, and the rivers that flow in darkness. Some of what you hear may surprise you, or simply let your mind wander in gentle directions as sleep finds you. Before we begin, if these calm explorations help you rest, or give you a quiet space at the end of your day, consider liking this video or subscribing to the channel. It helps others find their way here too, one peaceful night at a time. Now let your eyes close if they haven't already. Let the weight of the day dissolve, and let's descend together slowly into the deep. The ocean is not one place. It is layered like atmosphere, like memory. Near the surface, light pours through in golden shafts, warming the water, feeding algae, and setting the rhythm of life. But as you go deeper, the light begins to fade. First the reds disappear, then the oranges, then the yellows. By the time you reach 200 meters, even the blues have dimmed to near darkness. This is the edge of the sunlight zone, the twilight boundary where photosynthesis becomes impossible, and a different kind of ocean begins. Below this line lies the deep sea, a realm that makes up more than 90% of the ocean's livable space. It is the largest habitat on Earth, and it exists in near total darkness. The water here is cold, often just a few degrees above freezing. The pressure is immense, increasing by 1 atmosphere for every 10 meters of depth. At 1,000 meters, the pressure is 100 times what it is at the surface. At the deepest points, it is over 1,000 times greater. And yet, life persists. Not in spite of the darkness, but woven into it, adapted to it, shaped by it in ways that feel almost like poetry. There is no day or night in the deep ocean. The sun cycle, which governs so much of life on land and in shallow seas, does not reach here. Time moves differently when there are no sunrises to mark it, no seasons of light and warmth. The deep sea exists in a kind of eternal twilight, or in some places, eternal night. But that does not mean it is still. There are currents, slow and powerful, that circle the globe, carrying water, nutrients and heat across thousands of miles. There are tides felt even at great depths, subtle pulses in pressure and flow, and there is life, constantly moving, hunting, drifting, glowing. The deep ocean is not a void. It is a world quieter than ours, slower than ours, but no less intricate. Most of the deep ocean floor is covered in a fine, soft sediment called ooze. It sounds almost gentle, and in a way it is. This ooze is made from the remains of tiny organisms, plankton and algae and microbes that lived near the surface and then died, drifting down through the water column like snow. This is called marine snow, a continuous fall of organic particles slowly descending through the dark. It can take weeks or even months for a single flake of marine snow to reach the ocean floor, tumbling gently through the still water, passing through layer after layer of depth. When it finally settles, it joins countless others, building up over millennia into thick blankets of sediment. In some places, this ooze is hundreds of meters deep, a soft archive of life and time, preserved in darkness. The deep sea is not silent. For a long time, people imagined it that way, a vast quiet beneath the waves. But when scientists began listening, they discovered something different. The ocean hums. It clicks, it moans and whistles and rumbles. Some of these sounds come from animals, whales singing across ocean basins, shrimp snapping their claws, fish drumming their swim bladders. Other sounds come from the earth itself, undersea volcanoes erupting, tectonic plates grinding together, icebergs carving into the sea. Sound travels far in water, much farther than it does in air. And in the deep ocean, where there is no light to see by, sound becomes a primary sense. Animals use it to navigate, to communicate, to hunt. The deep sea is full of invisible conversations, echoes traveling through the dark. Bioluminescence is common in the deep ocean. In fact, it may be the most common form of communication in that lightless world. Creatures down there produce their own light, not from heat or fire, but from chemical reactions inside their bodies. Tiny organisms called dinoflagellates sparkle when disturbed. Jellyfish pulse with soft blue glows. Fish carry glowing lures or rows of light organs along their bellies. Squid flash patterns across their skin. Some animals use their light to attract prey, dangling glowing appendages like bait in the dark. Others use it to confuse predators, releasing clouds of luminous particles as they flee. Still others use it to communicate, signaling to mates or rivals in a language of flashes and pulses. In the deep sea, light is rare and precious, and the ability to make it is a kind of currency. One of the strangest things about bioluminescence is how widespread it is. Estimates suggest that up to 90% of deep-sea animals can produce light in some form. It is not an unusual adaptation, it is the norm. And yet, each species does it differently. Some glow constantly, a soft beacon in the dark. Others only light up when threatened or hunting. The colors vary too, though blue and green are most common because they travel farthest through water. Red light is rare in the deep sea, and some predators have evolved red bioluminescence as a kind of stealth adaptation, a flashlight only they can see, invisible to most other creatures. They shine red light onto their prey, illuminating it without alerting it. Like a hunter with night vision goggles, in a world that has never known red. The deep ocean is cold, but it is not frozen. Water at the surface freezes at 0 degrees Celsius, but deep seawater, heavy with salt and under immense pressure, remains liquid even at temperatures below freezing. In the deep sea, water temperatures hover between 1 and 4 degrees Celsius in most places, a cold that is constant and unrelenting. There are no warm currents here, no sun to offer relief, and yet animals thrive. Their bodies have adapted in extraordinary ways. Many deep-sea fish have proteins in their blood that act like antifreeze, preventing ice crystals from forming. Others have slowed their metabolisms to conserve energy in an environment where food is scarce. Life in the cold deep is not fast or frantic. It is patient, efficient, calibrated to a world where every calorie matters. Pressure is one of the defining forces of the deep ocean, and it shapes everything. At the surface, atmospheric pressure is roughly 1 bar, the weight of the air pressing down on us. For every 10 meters you descend into the ocean, the pressure increases by another bar. At 1,000 meters, the pressure is 100 bars. At 4,000 meters, it is 400. At the deepest point in the ocean, the Mariana Trench, the pressure exceeds 1,000 bars, more than 8 tons per square inch. To a human body, this pressure would be instantly fatal, crushing bone and tissue. But to the animals that live there, it is normal. Their bodies are made mostly of water, which is incompressible, so they do not feel crushed. Their cells are filled with adapted proteins and membranes that function under pressure. Some fish lack swim bladders entirely, organs that would collapse or rupture in the deep. They are soft, almost gelatinous, perfectly suited to their world. The deep ocean is not uniform. It has geography, just like the land. There are plains, vast and flat, stretching for thousands of miles. There are mountains, some taller than Everest, rising from the ocean floor in ridges and chains. There are valleys, trenches that plunge deeper than any canyon on land. And there are volcanoes, some active, spewing lava and mineral-rich water into the cold dark. The mid-ocean ridge, a massive underwater mountain range, winds through every ocean on Earth, a continuous seam where tectonic plates pull apart and new seafloor is born. It is the longest mountain range on the planet, over 60,000 kilometers long, and most of it has never been seen by human eyes. The deep ocean floor is a landscape, hidden and huge, shaped by forces we are only beginning to understand. Hydrothermal vents are among the strangest and most important features of the deep ocean. These are cracks in the sea floor where superheated water, sometimes exceeding 300 degrees Celsius, pours out from beneath the Earth's crust. The water is loaded with minerals, sulfur, iron, and other compounds dissolved from the hot rock below. When this scalding water meets the frigid ocean, the minerals precipitate out, forming towering chimneys of rock that can grow several meters tall. Some of these chimneys are white or grey, others are black, billowing dark clouds of mineral particles, earning them the name black smokers. The water around these vents shimmers with heat, a strange sight in the deep cold. And despite the extreme temperatures, despite the toxic chemicals, life thrives here. In fact, hydrothermal vents support some of the most densely populated ecosystems in the deep sea. The reason life flourishes around hydrothermal vents is chemosynthesis, a process that replaces photosynthesis in the sunless deep. Instead of using sunlight to create energy, certain bacteria use the chemicals in vent water, particularly hydrogen sulfide, to fuel their metabolism. These bacteria form the base of the food chain, living in dense mats on rocks or inside the bodies of larger animals. Tube worms, some over 2 meters long, have no mouth or digestive system. Instead, they house chemosynthetic bacteria inside specialized organs, and the bacteria provide them with nutrients. Clams, mussels, shrimp, and crabs cluster around vents, feeding on bacteria or on each other. Fish patrol the edges. Octopuses hunt in the warm water. These ecosystems exist entirely independently of the sun, powered by the Earth's internal heat. They are a reminder that life is more flexible, more inventive than we once believed. Marine snow is the primary source of food in much of the deep ocean, and it falls constantly, slowly, like a gentle drift of organic particles through dark water. It is made of many things: dead plankton mostly, but also fecal pellets from animals near the surface, fragments of algae, mucus from jellyfish, molted shells, and bits of decomposing tissue. As these particles sink, they clump together, forming larger aggregates that fall faster. Some are tiny, barely visible specks. Others are several centimeters across, delicate and fragile, held together by sticky substances secreted by bacteria. This snow drifts down through the water column, passing through different zones of depth, each with its own community of creatures waiting to feed. Some animals intercept the snow as it falls, filtering it from the water with feathery appendages or mucus nets. Others wait on the seafloor, sifting through the sediment for whatever has settled. Marine snow is not abundant, but it is constant, a thin rain of energy from above. Not all marine snow reaches the bottom. Much of it is consumed on the way down, picked apart by bacteria, broken apart by currents, or eaten by animals drifting in the midwater. By the time it reaches the deep sea floor, only a small fraction of the organic matter that began at the surface remains. This is one reason why food is so scarce in the deep ocean. Life there exists on the leftovers of the leftovers, on the scraps that manage to escape the hungry layers above. And yet even these scraps are enough. Animals in the deep have evolved to survive on remarkably little, stretching every calorie, waiting patiently between meals, sometimes for weeks or months. The twilight zone, also called the mesopelagic zone, lies between 200 and 1,000 meters deep. It is the transition between the sunlit surface and the true deep sea, a place where faint traces of light still penetrate, but not enough to sustain photosynthesis. This zone is home to some of the strangest and most abundant animals in the ocean. Lanternfish, small silvery fish with rows of glowing photophores along their bodies, gather here in enormous schools, numbering in the billions. They migrate upward every night, rising toward the surface to feed, and then descend again before dawn, a daily journey called DL vertical migration. This migration is one of the largest movements of biomass on the planet, involving countless tons of animals traveling hundreds of meters every day. It connects the surface and the deep, transferring energy downward and cycling nutrients upward, a kind of biological conveyor belt. Many animals in the twilight zone have large eyes, adapted to capture even the faintest glimmers of light. Their eyes are often tubular, pointing upward, scanning the dim water above for silhouettes of prey or predators. Some fish have eyes so sensitive they can detect bioluminescence from hundreds of meters away. Others have given up on vision entirely, their eyes reduced to useless remnants, relying instead on other senses: touch, smell, electroreception. In the twilight zone, vision is useful but not essential. The line between light and dark is blurry, and animals navigate it in different ways, some clinging to the last traces of the sun, others embracing the darkness below. Gelatinous animals are common in the deep ocean. Jellyfish, comb jellies, salps, siphonophores, all soft-bodied, translucent, drifting through the water like living glass. Their bodies are more than 95% water, which makes them nearly neutrally buoyant, requiring little energy to stay afloat. Some are small, no larger than a coin. Others are enormous, trailing tentacles tens of meters long, longer than a blue whale. These tentacles are lined with stinging cells or sticky pads, capturing small fish, crustaceans, and plankton as the animal drifts passively through the water. Gelatinous animals are often bioluminescent, glowing softly as they pulse through the dark, their bells contracting and expanding in slow rhythm. They are fragile, easily torn apart by nets or rough handling, and because of this, they were long overlooked by scientists. But in recent years, remotely operated vehicles and gentle collection methods have revealed just how abundant and diverse these animals are. Siphonophores are among the strangest creatures in the deep sea. They look like a single animal, but they are actually colonies, made up of thousands of individual organisms called zooids, each specialized for a different function. Some zooids form the float or the stem. Others are responsible for feeding, trailing long tentacles lined with stinging cells. Still others handle reproduction or defense. Together, they function as one coordinated organism, drifting through the midwater, capturing prey and growing longer. Some siphonophores can reach lengths of 30 or even 40 meters, making them among the longest animals on Earth. They are delicate, almost invisible in the water, but they are efficient predators, their tentacles creating curtains of death in the dark. The midnight zone, or bathypelagic zone, extends from 1,000 meters to 4,000 meters deep. Here, there is no light at all, not even the faintest trace from the surface. The darkness is total, absolute, broken only by the occasional flash of bioluminescence. The water is uniformly cold, hovering just above freezing. Food is scarce, pressure is immense, and yet life continues. Fish here are often small, black or red in color to avoid reflecting what little bioluminescent light exists. Their bodies are soft, their bones thin and flexible. Many have enormous mouths and stretchy stomachs, allowing them to swallow prey larger than themselves, a necessary adaptation in a place where meals are rare. Some fish have long thread-like fins that help them sense vibrations in the water, detecting the movement of prey or predators from a distance. Life in the midnight zone is slow, solitary, and patient. One of the most famous deep-sea fish is the anglerfish, and there are many species, each strange in its own way. Female anglerfish have a long spine protruding from their heads, tipped with a glowing lure made of bioluminescent bacteria. They wave this lure in the dark, attracting curious prey, which they swallow with their huge, fang-lined mouths. Males, however, are much smaller, sometimes 100 times smaller than the females, and in many species they do not hunt at all. Instead, they attach themselves to a female, biting into her skin and fusing with her body. Over time, the male loses his eyes, his organs, everything except his reproductive system. He becomes a permanent parasite sustained by the female's bloodstream, ready to fertilize her eggs when the time comes. It is a bizarre form of reproduction born from the challenges of finding a mate in the vast, dark ocean. Gulper eels, also called pelican eels, are another strange deep-sea fish. They have enormous mouths, hinged jaws that can open incredibly wide, and long whip-like tails that taper to a thin point. Their stomachs can expand to hold prey much larger than the eel itself, though they likely feed more often on small crustaceans and fish. Despite their fearsome appearance, gulper eels are not fast swimmers. They drift slowly through the midwater, mouths agape, waiting for food to come to them. Some species have a glowing organ at the tip of their tail, which they may use to lure prey or communicate. Their bodies are dark, almost black, and their skin is loose and flexible. suited to a life of low energy and rare feeding. The deep ocean is home to giant isopods, crustaceans that look like enormous pillbugs or woodlice. They can grow up to 30 centimeters long, with hard segmented shells and multiple pairs of legs. They scuttle across the seafloor, scavenging on whatever they find: dead fish, whale falls, bits of organic matter. Giant isopods are opportunistic feeders, able to survive for long periods without food, and when they do find a meal, they gorge themselves, sometimes eating so much they can barely move. They are ancient-looking creatures, unchanged for millions of years, perfectly adapted to the cold, dark, food-poor world of the deep sea. Vampire squid are not true squid, despite their name. They belong to their own unique order, somewhere between squid and octopus. They are small, rarely longer than 30 centimeters, with a soft, gelatinous body covered in light-producing organs called photophores. When threatened, the vampire squid can invert its cape-like webbing, pulling it over its body and turning itself inside out, revealing rows of fleshy spines. It can also release clouds of bioluminescent mucus, glowing particles that confuse predators while the squid escapes into the dark. Despite their sinister name and appearance, vampire squid are not aggressive hunters. They feed primarily on marine snow, using long, thread-like filaments to collect falling particles. A surprisingly gentle diet for such a dramatic animal. Deep-sea octopuses are often pale, ghostly, with soft bodies and large eyes. Some species brood their eggs for years, the longest known egg-brooding period of any animal. One species, observed by scientists using a remotely operated vehicle, was seen guarding her eggs for over 4 years, never leaving them, not even to feed. By the time the eggs hatched, the mother had withered, her skin pale and torn, her body emaciated. She died shortly after her young emerged, having sacrificed everything to protect them. It is a quiet, devastating form of devotion, played out in the cold and dark, far from any witness except the occasional robot and camera. The abyssal zone stretches from 4,000 to 6,000 meters deep, covering much of the ocean floor. It is a place of flat, featureless plains, soft sediment, and near-freezing temperatures. The pressure here is immense, hundreds of times greater than at the surface. Life is sparse, but not absent. Sea cucumbers, soft-bodied relatives of starfish and sea urchins, crawl slowly across the seafloor, feeding on organic matter in the mud. Some leave trails behind them, long furrows in the sediment that can be seen in seafloor images, evidence of their slow passage. Brittle stars, with their long, spindly arms, cling to rocks or burrow into the ooze. Amphipods, small shrimp-like crustaceans, scuttle through the sediment, scavenging. Fish are rare at these depths, but not unknown. Rat-tail fish, also called grenadiers, patrol the bottom, their long tapering bodies ghosting through the dark. The Hadal Zone is the deepest part of the ocean, found in ocean trenches that plunge below 6,000 meters. The name comes from Hades, the ancient Greek underworld, and it is fitting. These trenches are the most extreme environments on Earth, deeper than Mount Everest is tall, darker than any cave, colder than any winter, and under pressures that would crush almost anything. And yet, life exists even here. Amphipods, pale and translucent, swarm in great numbers, feeding on whatever organic matter sinks to these depths. Snailfish, small and gelatinous, swim slowly through the trench, their bodies adapted to pressures that would liquefy most other fish. Microbes coat the rocks and sediment, breaking down organic material and recycling nutrients. The Hadal Zone is not lifeless, it is simply life at its most extreme, pushed to the very edge of what is possible. The Mariana Trench is the deepest place in the ocean, and the deepest place on Earth. Its lowest point, called Challenger Deep, lies nearly 11,000 meters below the surface. Only a handful of people have ever been there, and each descent is an extraordinary feat of engineering and courage. The water is near freezing. The pressure is over 1,000 times atmospheric, and yet when cameras and submersibles reach the bottom, they find life. Amphipods, sea cucumbers, microbes, even fish, living in a place we once believed was too hostile for anything to survive. Plastic bags and wrappers have also been found there, a sobering reminder that human influence reaches even the most remote corners of the planet. Whale falls are one of the most important sources of food in the deep ocean. When a whale dies and its body sinks to the seafloor, it brings with it an enormous amount of organic matter, sometimes tens of tons of flesh, bone, and blubber. This is a feast in a place where food is scarce, and it attracts animals from across the surrounding area. Within hours, scavengers arrive. Hagfish, eels with no jaws and slimy skin, burrow into the carcass, feeding from the inside out. Sleeper sharks, slow-moving giants, tear chunks of flesh from the body. Crabs and amphipods swarm the bones. Over months and years, the carcass is picked clean, but even then, the whalefall continues to support life. Bacteria colonize the bones, breaking down the lipids stored inside, and these bacteria in turn support worms, clams, and other creatures in a process that can last for decades. A single whale fall can sustain a localized ecosystem for 50 years or more, a deep-sea oasis built from death. Some deep-sea creatures are incredibly long-lived. The Greenland shark, which inhabits the cold waters of the North Atlantic and Arctic, is thought to be the longest-lived vertebrate on Earth. Some individuals may live for over 400 years, growing slowly, maturing late, and moving through the dark water with patient, unhurried grace. Their eyes are often clouded by parasites, small crustaceans that attach to the cornea and dangle in front of the shark's vision. Yet the sharks do not seem bothered. They navigate by smell and electroreception, drifting through the deep, hunting fish and scavenging carrion, their lives stretching across centuries. A Greenland shark alive today may have been born before the Industrial Revolution, swimming through wars, through human progress, through changes it could never perceive, silent and ancient. Deep-sea corals also live for centuries, sometimes thousands of years. Unlike the colourful corals of shallow reefs, which rely on symbiotic algae and sunlight, deep-sea corals survive in total darkness, feeding on plankton and organic particles drifting past in the current. They grow incredibly slowly, sometimes less than a millimetre per year, and they build reefs and forests on the seafloor that provide habitat for countless other species. Black corals, bamboo corals, and precious corals form intricate structures, their branches reaching into the water like frozen trees. Some deep-sea coral colonies are over 4,000 years old, older than the pyramids, older than written language, silent witnesses to a history no human has ever seen. Glass sponges, found in the deep ocean, are among the most beautiful and strange of all sea creatures. Their skeletons are made of silica, the same material as glass, and they form delicate, lattice-like structures that look almost crystalline. These sponges can grow to enormous sizes, some forming reefs that stretch for kilometers. They filter water through their bodies, extracting bacteria and organic particles, and they grow slowly, sometimes living for thousands of years. In some parts of the ocean, glass sponge reefs create complex three-dimensional habitats, providing shelter for fish, shrimp, and other animals. The sponges themselves are sessile, rooted in place, but their presence transforms the sea floor, turning barren mud into a fragile, glittering forest. Tube worms are another iconic deep-sea creature, especially around hydrothermal vents. The giant tube worm, Riftia pachyptila, can grow over 2 meters long, its body encased in a white tube made of chitin. A bright red plume extends from the top, used to absorb oxygen and hydrogen sulfide from the water. The worm has no mouth, no stomach, no digestive system. Instead, it relies entirely on chemosynthetic bacteria living in a specialized organ inside its body. The worm provides the bacteria with raw materials, and the bacteria provide the worm with nutrients. This relationship is so close, so essential that neither can survive without the other. Tube worms grow quickly, far faster than most deep-sea animals, fueled by the constant flow of energy from the vent. They live for decades, their red plumes waving gently in the warm, chemical-rich water, symbols of life thriving in the most unlikely places. Chemosynthetic ecosystems exist in other places too, not just at hydrothermal vents. Cold seeps, where methane or hydrogen sulfide leaks from the seafloor, also support dense communities of life. Clams, mussels, and tube worms cluster around these seeps, feeding on bacteria that metabolize the chemicals. Some cold seeps occur along continental margins, where organic rich sediments release methane as they decompose. Others form where tectonic activity fractures the sea floor, allowing gases to escape. These seeps can persist for thousands of years, supporting stable communities in the otherwise food-poor deep sea. Like hydrothermal vents, cold seeps are windows into a different kind of life, one not powered by the sun but by the earth itself. Methane hydrates, also called methane ice, form in deep-sea sediments under high pressure and low temperature. They look like ice, but they are made of methane molecules trapped in a cage of frozen water. Vast deposits of methane hydrate lie buried beneath the sea floor, especially along continental slopes, and they represent one of the largest reservoirs of organic carbon on Earth. If these hydrates melt due to warming temperatures or changes in pressure, the methane is released into the water and eventually into the atmosphere, where it acts as a powerful greenhouse gas. This is one reason scientists are concerned about deep-sea warming. The deep ocean feels remote, but it is connected to the climate, to the atmosphere, to the surface. What happens in the deep does not stay there. The deep ocean plays a critical role in regulating Earth's climate. It absorbs enormous amounts of carbon dioxide from the atmosphere, acting as a carbon sink. Phytoplankton near the surface take in carbon dioxide during photosynthesis, and when they die, some of that carbon sinks to the deep ocean, where it can remain locked away for centuries or millennia. The ocean also absorbs and stores heat, slowing the rate of atmospheric warming. Deep ocean currents, driven by differences in temperature and salinity, circulate this heat around the globe, redistributing it from the equator to the poles. This circulation, sometimes called the global conveyor belt, influences weather patterns, sea level, and marine ecosystems. The deep ocean is not separate from the world above. It is part of the same system, slow and vast, but essential. Seamounts are underwater mountains, remnants of volcanic activity, rising from the deep sea floor but not quite reaching the surface. There are tens of thousands of seamounts scattered across the ocean floor, and they serve as oases in the deep. Currents sweeping over a seamount are forced upward, bringing nutrient-rich water from the depths toward the surface. This upwelling supports dense communities of plankton, which in turn attract fish, sharks, whales, and seabirds. Seamounts are biodiversity hotspots, home to deep-sea corals, sponges, and species found nowhere else. Many seamounts remain unmapped and unexplored, and some harbor species unknown to science. They rise like islands from the abyss, silent and isolated, each one a small world within the larger ocean. Canyons carve through the continental slope, channeling sediment and organic matter from shallow waters down to the deep sea. These canyons can be enormous, deeper and wider than the Grand Canyon, and they serve as conduits, funneling food to the deep. Turbidity currents, underwater avalanches of sediment rush down these canyons at high speed, carrying everything in their path. When these currents reach the abyssal plain, they spread out, depositing layers of sediment in fan-shaped formations. Animals living in and around submarine canyons benefit from the steady flow of organic material, and these areas are often more densely populated than the surrounding seafloor. Canyons are highways in the deep, connecting the shallow and the deep in a network of flowing sediment and life. The ocean floor is constantly being created and destroyed. At mid-ocean ridges, tectonic plates pull apart, and magma from the Earth's mantle rises to fill the gap, creating new seafloor. This process, called seafloor spreading, adds new crust at a rate of a few centimeters per year, slow by human standards but relentless over geological time. At subduction zones, where one tectonic plate slides beneath another, old seafloor is drawn down into the mantle, melting and recycling. The ocean floor is not ancient. Most of it is less than 200 million years old, young compared to the continents. The deep ocean is a place of creation and destruction, constantly renewing itself, driven by forces deep within the Earth. Earthquakes and volcanic eruptions occur frequently in the deep ocean, though most go unnoticed by humans. The mid-ocean ridge system is seismically active, with thousands of small quakes occurring every year as magma pushes upward and plates shift. Underwater volcanoes, or seamounts, erupt periodically, spewing lava into the cold water, where it cools rapidly into pillow-shaped formations. Some eruptions are detected by hydrophones, underwater microphones that listen for the low-frequency rumble of volcanic activity. Other eruptions are discovered only later, when submersibles or seafloor mapping reveal fresh lava flows or new seamounts. The deep ocean is not geologically dead. It is active, restless, shaped by the same forces that build mountains and split continents. Brine pools are one of the strangest features of the deep seafloor. These are pockets of extremely salty water, much saltier than the surrounding seawater, that collect in depressions on the ocean floor. The brine is denser than normal seawater, so it does not mix. Instead, it forms a distinct layer with a sharp boundary that looks almost like a shoreline. Submersibles descending into a brine pool report the sensation of crossing a surface, as if moving from water into a different liquid. Brine pools are often anoxic, meaning they contain little or no oxygen, and they are toxic to most marine life. Animals that wander into a brine pool by mistake often die, their bodies preserved in the salty water, and yet life exists even here. Certain bacteria and archaea thrive in the brine, metabolizing the chemicals and forming mats on the shore. Mussels cluster around the edges, housing chemosynthetic bacteria in their tissues, feeding on the chemical energy released by the brine. Cold seeps and brine pools are sometimes found together, and in these places, the seafloor becomes a patchwork of strange habitats. Mussels, clams, and tube worms form dense clusters around the seeps, while the brine pools lie nearby, dark and still, rimmed with bacterial mats. The landscape is eerie, almost alien, a place of contrasts, where life and death exist side by side, where the toxic and the fertile are separated by mere meters. Scientists studying these environments are still trying to understand the relationships between the different communities, how they interact, how they evolved, and what they can tell us about the limits of life. Hydrothermal vents do not last forever. They can be active for decades or even centuries, but eventually the geological activity that powers them shifts or stops. When a vent dies, the heat fades, the chemicals stop flowing, the vent community collapses, the tube worms die, the bacteria disappear, the crabs and shrimp move on or starve. Over time, the vent chimney crumbles and the seafloor returns to the cold, dark, food-poor state that defines most of the deep ocean. But elsewhere, new vents open, and life colonizes them quickly, carried by larvae drifting in the currents. Vent ecosystems are ephemeral, islands of abundance in a sea of scarcity, constantly appearing and disappearing across the ocean floor. They are temporary, but life has learned to move with them, to find them, to begin again. The deep ocean is full of microbes, and they are the foundation of almost every ecosystem there. Bacteria and archaea live in the water, in the sediment, inside animals, on rocks, in hydrothermal fluids, everywhere. They break down organic matter, recycle nutrients, produce chemicals, and support larger organisms. Some deep-sea microbes can survive in conditions that would kill almost any other form of life. They thrive in boiling water, in acidic or alkaline environments, in complete darkness, under crushing pressure. They metabolize sulfur, methane, hydrogen, iron, and other compounds that are toxic to most life. These extremophiles, as they are called, expand our understanding of what life can be, where it can exist, and how it might have originated. Studying deep-sea microbes has implications not just for biology, but for astrobiology, the search for life on other worlds. Some scientists believe that life on Earth may have begun at hydrothermal vents. The theory suggests that the warm, chemical-rich water of early Earth's ocean vents provided the energy and raw materials needed for the first simple cells to form. The vents create natural chemical gradients, boundaries between hot and cold, acidic and alkaline, conditions that could have driven the reactions necessary for life. The deep ocean, once thought of as barren and lifeless, may actually be the cradle of all life on Earth. It is a humbling thought that the darkness and pressure we once feared may be where everything began, where the first spark of metabolism flickered into existence, in the warmth of a vent, in the cold embrace of the deep. Many deep-sea animals are red or black in color, adaptations to a world without sunlight. Red light does not penetrate deep water, so a red animal appears black in the deep sea, effectively invisible. Black animals absorb all wavelengths of light, including bioluminescence, preventing reflections that might give away their position. Some fish and shrimp are so dark they absorb over 99% of light that hits them, among the blackest living things known. This ultra-black coloration is achieved through specialized skin structures that trap light, a form of natural camouflage more effective than any human-made stealth technology. In the deep ocean, being seen is often being eaten, and evolution has crafted bodies that vanish into the dark. Counter-illumination is another form of camouflage used by midwater animals. Many fish and squid have light organs on their undersides, which they use to match the faint downwelling light from above. When a predator looks up, it sees not a dark silhouette but a glow that blends with the background, rendering the prey nearly invisible. The animal constantly adjusts the intensity of its light organs, dimming or brightening them as the ambient light changes, a dynamic camouflage that requires active control. It is a silent, automatic process, light sculpting shadow, erasing form, allowing the animal to drift unseen through the twilight. The deep ocean is largely unexplored. Despite covering more than half the planet's surface, we have mapped less than 20% of the seafloor in high resolution. We have sent more people to the moon and to the deepest parts of the ocean. Much of what we know comes from a few submersible dives, remotely operated vehicles, and towed cameras. Glimpses into a vast and mostly unknown world. Every expedition to the deep sea discovers new species, new behaviors, new ecosystems. There is so much we do not know, so much waiting to be found, so many questions we have not even thought to ask yet. The deep ocean is the last great frontier on Earth, closer than space, but in many ways just as remote. Sound travels differently in water than in air. It moves faster, about 4 times faster, and it can travel much farther without losing strength. In the deep ocean, where light does not penetrate, sound becomes the primary way to sense the environment. Whales use low-frequency calls that can travel across entire ocean basins, and before the noise of ships filled the sea, a whale's song could be heard thousands of kilometers away. Fish and invertebrates also produce sound, clicking, grunting, drumming, and buzzing, creating an acoustic landscape that is rich and complex. Scientists use hydrophones to listen to the deep, recording the sounds of animals, of geological activity, of ice, and of human activity. Listening reveals a hidden dimension of the ocean, a soundscape we are only beginning to understand. Deep-sea fish often have poor swimming abilities. In a place where food is scarce and energy must be conserved, many fish have evolved to be slow, passive, drifting with the currents rather than swimming actively. Their muscles are reduced, their bones thin, their bodies soft and gelatinous. Some fish simply hover in place, waiting for prey to come to them, using minimal energy. This is a stark contrast to the fast, muscular fish of the surface, but it is a successful strategy in the deep. Speed is less important than patience, and efficiency is everything. Life in the deep ocean is not about quick bursts of activity, but about enduring, about lasting through the long empty stretches between meals. Some deep-sea fish have bioluminescent lures that mimic prey. The anglerfish's glowing lure, dangling in front of its mouth, looks like a small glowing creature, perhaps a copepod or a shrimp. Curious fish or squid, drawn to the light, swim closer to investigate, and the anglerfish strikes, swallowing them whole. Other fish use lures in different ways. Some dangle them from their lower jaws. Others have lures inside their mouths, visible only when the fish opens wide, a glowing trap waiting in the dark. These lures are powered by bioluminescent bacteria, living symbionts that the fish cultivates, feeding them and housing them in specialized organs in exchange for light. Deep-sea predators often have large teeth relative to their body size, and these teeth are sometimes hinged or depressible, allowing the predator to swallow prey larger than itself. The viperfish, for example, has fangs so long they do not fit inside its mouth. When the fish closes its jaws, the teeth extend outside, curving back toward its eyes. When it strikes, it opens its mouth wide, the lower jaw dropping down and the skull tilting back, creating a gaping tunnel that engulfs the prey. The fangs then clamp down, preventing escape. It is a brutal, efficient design, born from a world where every meal counts and opportunities are rare. Dragonfish are another group of deep-sea predators with fearsome adaptations. They have long bodies, large heads, and mouths full of needle-like teeth. Some species have a bioluminescent barbel hanging from their chin, which they wave to attract prey. Others have light organs below their eyes, which they can flash on and off, scanning the water for movement. Some dragonfish produce red bioluminescence, a rare color in the deep sea, and they have special pigments in their eyes that allow them to see red light, giving them a private wavelength invisible to most other animals. They hunt in darkness with their own secret spotlight, seeing without being seen. Hatchetfish are small, laterally compressed fish with large upward-pointing eyes and rows of bioluminescent organs along their bellies. They live in the twilight zone, where they use counter-illumination to hide from predators below. Their bodies are shaped like hatchets, thin and deep, and they drift motionless in the water, conserving energy. Despite their delicate appearance, hatchetfish are common and widespread, one of the most abundant groups of fish in the midwater. They feed on small crustaceans and plankton, migrating upward at night to feed in richer waters and descending during the day to avoid predators. They are part of the Great Daily Migration, a quiet rhythm that pulses through the ocean, unseen by those on the surface. Barrel-eye fish have transparent heads, a feature so strange it seems almost fictional. Their eyes are tubular, pointing upward, housed inside a fluid-filled dome of transparent tissue. This allows the fish to look up through its own head, scanning the water above for the silhouettes of prey. The eyes are highly sensitive, capable of detecting faint light, and they can rotate, allowing the fish to shift its gaze. The transparent dome protects the eyes while allowing light to pass through. When the barrel eye was first discovered, scientists thought the dome was damaged during collection, not realizing it was a natural feature. It is one of many reminders that the deep ocean holds creatures stranger than we can imagine. Blobfish, famous for their unfortunate appearance in photographs, look very different in their natural habitat. At depth, under immense pressure, the blobfish's gelatinous body is normal, streamlined, suited to a life of hovering just above the seafloor, waiting to ambush small invertebrates. But when brought to the surface, the pressure drops and the fish's body expands and sags, creating the droopy, sad appearance that made it famous. It is not fair to judge a deep-sea creature by how it looks out of its element, in a medium it was never meant to inhabit. The blobfish is adapted perfectly for its world, even if that world is alien to us. Many deep-sea animals exhibit gigantism, growing much larger than their shallow water relatives. Giant squid, giant isopods, giant amphipods, giant sea spiders, all disproportionately large compared to similar species in warmer, shallower waters. This phenomenon, called deep-sea gigantism, is not fully understood, but it may be related to the cold temperatures, which slow metabolism and allow animals to grow for longer periods, or to the scarcity of food, which favors larger animals with greater energy reserves. It may also be related to pressure, oxygen availability, or the absence of predators. Whatever the cause, the deep ocean is home to giants, creatures that dwarf their cousins above. Giant squid are among the most famous and mysterious creatures of the deep sea. For centuries, sailors told stories of kraken, enormous squid that could drag ships beneath the waves. These stories were dismissed as myth, But in the 19th and 20th centuries, dead giant squid began washing ashore, proof that something large and strange lived in the deep. Giant squid can reach lengths of over 12 meters, with eyes the size of dinner plates, the largest of any animal. They hunt in the midwater, using their long tentacles to capture fish and smaller squid, and they are hunted in turn by sperm whales, which dive deep to pursue them. For many years, no one had ever seen a living giant squid in its natural habitat. Then, in the early 21st century, Japanese scientists captured the first video footage of a giant squid in the wild, a ghostly creature glowing in the lights of a submersible, moving with surprising grace. The mystery is not fully solved, but it has been glimpsed. Colossal squid are even larger than giant squid, and perhaps even more mysterious. They live in the deep waters around Antarctica, and almost everything we know about them comes from specimens caught in fishing nets or found in the stomachs of sperm whales. Colossal squid have shorter arms and longer mantles than giant squid, and their tentacles are lined with sharp swiveling hooks as well as suckers. They are thought to be ambush predators, drifting in the water and striking when prey comes close. No one has ever filmed a living colossal squid, and much about their behavior, lifespan, and ecology remains unknown. They are giants of the deep, rarely seen, rarely studied, haunting the cold southern ocean like ghosts. Sperm whales are the deepest diving mammals, capable of descending over 2,000 meters and holding their breath for over an hour. They hunt squid in the deep, using echolocation to navigate and find prey in total darkness. Their clicks are among the loudest sounds produced by any animal, focused beams of sound that can stun or disorient squid, making them easier to catch. Sperm whales have enormous heads, filled with a waxy substance called spermaceti, which may help them control their buoyancy during deep dives. They are social animals, living in family groups, and they have complex vocalizations, patterns of clicks that may serve as identification or communication. When a sperm whale dives, it disappears into the deep for long stretches, silent and invisible, a warm-blooded visitor to a cold, alien world. Beaked whales are also deep divers, though they are less well known than sperm whales. There are more than 20 species of beaked whales, and some are so rarely seen that we know them only from a handful of strandings. They dive to depths exceeding 3,000 meters, chasing squid and deep-sea fish. One species, Cuvier's beaked whale, holds the record for the deepest and longest dive ever recorded, nearly 3,000 meters and over 2 hours underwater. How they survive such dives, how they avoid decompression sickness, and what they do in the deep are questions scientists are still trying to answer. Beaked whales are elusive, surfacing only briefly to breathe before diving again, spending most of their lives in a realm we cannot follow. Deep-sea fish often have reduced or absent swim bladders. Swim bladders are gas-filled organs that help fish control their buoyancy, but at great depths, the pressure makes gas-filled structures problematic. Filling a swim bladder with gas at high pressure requires enormous energy, and if the fish ascends too quickly, the gas expands, causing the bladder to rupture. Many deep-sea fish have lost their swim bladders entirely or replaced them with lipid-filled structures which are incompressible. These fish are neutrally buoyant without needing gas, and they can move up and down in the water column without difficulty. It is one of many adaptations that allow life to persist under pressure, a quiet solution to a harsh environment. Some deep-sea fish have light organs that they can control, turning their bioluminescence on and off at will. This allows them to signal, to camouflage, to hunt, or to startle predators. Flashlight fish have large light organs beneath their eyes filled with bioluminescent bacteria, and they can cover these organs with a flap of skin, effectively blinking the light on and off. They use this ability to communicate with others of their kind, flashing in patterns that may indicate alarm, courtship, or territory. Other fish have more complex arrangements, with multiple light organs in different locations, each controllable independently, allowing for intricate light displays in the darkness. The deep ocean is home to many species of jellyfish, some of which are enormous. The lion's mane jellyfish, though more common in cold surface waters, can have tentacles over 30 meters long. Deep-sea jellyfish are often smaller but no less strange. Some are bell-shaped, others are elongated, and still others are so delicate they disintegrate when disturbed. Many deep-sea jellyfish are bioluminescent, pulsing with light as they drift through the water. They feed on plankton, small fish, and other jellyfish, capturing prey with stinging tentacles or sticky mucus. They are passive drifters carried by currents, but they are also predators, efficient and patient, waiting for food to come to them. Comb jellies, or ctenophores, are superficially similar to jellyfish, but belong to a completely different group. They do not sting. Instead, they have sticky cells on their tentacles or feeding lobes, which they use to capture prey. Comb jellies are named for the rows of cilia that run along their bodies, which beat in coordinated waves, propelling them through the water. These cilia diffract light, creating shimmering rainbows of color, though in the deep sea, where there is no light to diffract, this display goes unseen. Many comb jellies are bioluminescent, glowing with soft blue or green light. They are delicate, almost entirely water, but they are surprisingly efficient predators, consuming large quantities of plankton and small animals. Salps are gelatinous, barrel-shaped animals that filter plankton from the water. They are tunicates, relatives of sea squirts, and they are more closely related to vertebrates than to jellyfish, though they do not look it. Salps can form long chains, with dozens or even hundreds of individuals linked together, pulsing in unison as they move through the water. They reproduce rapidly, sometimes forming enormous blooms that stretch for kilometers, dense swarms of transparent bodies drifting through the ocean. Salps feed efficiently, filtering large volumes of water, and they produce dense fecal pellets that sink quickly, transporting carbon to the deep sea. They are a crucial part of the ocean's carbon cycle, moving organic material from the surface to the depths. Larvaceans are another type of tunicate, small and tadpole-shaped, with a long tail they use to swim. They build elaborate mucus houses around themselves, intricate filters that trap plankton from the water. As water flows through the house, plankton are caught in the mucus, and the larvacean eats them. When the house becomes clogged, the larvacean abandons it and builds a new one. The discarded houses drift downward, contributing to marine snow, carrying trapped plankton and organic matter to the deep. Larvaceans are tiny, often just a few millimeters long, but they are abundant, and their mucus houses play a significant role in moving carbon from the surface to the deep ocean. The deep ocean is not entirely dark. Aside from bioluminescence, there are other faint sources of light. Geothermal radiation from hydrothermal vents emits a dim glow, mostly in the infrared spectrum, invisible to human eyes but potentially detectable by specialized animals. Cosmic rays and radioactive decay in seawater produce tiny flashes of light, Cherenkov radiation, though these are extremely faint. Some scientists have speculated that deep-sea animals with highly sensitive eyes might be able to detect even these feeble glimmers, using them to navigate or sense their surroundings. The deep ocean is not a place of total darkness, but of near darkness, punctuated by rare and subtle sources of light, most of which we cannot see. Bioluminescence serves many purposes in the deep sea, and one of the most important is communication. Many species use specific patterns of light to identify themselves, to attract mates, or to signal alarm. Some squid have light organs arranged in species-specific patterns, like name tags written in light, allowing individuals to recognize each other in the dark. Flashlight fish gather in groups at night, flashing synchronously, a coordinated display that may help them stay together or confuse predators. Some deep-sea shrimp release clouds of bioluminescent particles when threatened, creating a glowing decoy that distracts predators while the shrimp escapes. Light in the deep ocean is a language, subtle and varied, spoken by creatures we are only beginning to understand. The deep ocean is full of parasites. In a world where food is scarce, parasitism is a viable strategy, and many deep-sea animals have evolved to live on or inside others. Some copepods attach to fish, feeding on their blood or tissue. Some isopods burrow into the mouths of fish, replacing the fish's tongue and feeding on mucus and blood. Some barnacles infest crabs, sending root-like tendrils throughout the host's body, castrating it and controlling its behavior. Parasitism is common in the deep sea, perhaps more common than in shallow waters, because it allows an organism to exploit a host's energy without having to hunt or forage in a food-poor environment. It is a grim strategy, but an effective one. Some deep-sea fish are hermaphrodites, possessing both male and female reproductive organs. This adaptation increases the chances of successful reproduction in a vast, sparsely populated environment. When two individuals meet, they can both produce offspring, doubling the reproductive potential of the encounter. Other deep-sea fish have highly skewed sex ratios, with many more females than males, or vice versa. Some species have males that are parasitic, attaching to females permanently and functioning only as sperm providers. Reproduction in the deep sea is shaped by the challenges of the environment, by the difficulty of finding a mate in the dark, and by the need to make every encounter count. Deep-sea animals often have slow metabolisms, a consequence of the cold temperatures and low food availability. Chemical reactions slow in cold water, and animals in the deep sea have adapted to function at these slower rates. Their heartbeats are slow, their digestion is slow, their movements are deliberate. This slow pace of life allows them to survive on very little food, stretching their energy reserves over long periods. But it also means they grow slowly, reproduce infrequently, and are vulnerable to overfishing or disturbance. A deep-sea fish that takes decades to reach maturity cannot quickly recover from population losses. The slow metabolism that allows life in the deep is also a fragility, a vulnerability to change. Some deep-sea creatures are transparent, their bodies nearly invisible in the water. Transparency is a form of camouflage, effective in the midwater where there is nowhere to hide. A transparent animal is difficult to see, whether from above, below, or the side, because light passes through it without being absorbed or reflected. However, achieving true transparency is difficult. Eyes, guts, and other organs are often opaque, and they can give the animal away. Some transparent animals have evolved ways to hide these structures, using reflective coatings, pigments, or specialized tissues that scatter light. Others simply minimize their opaque parts, keeping them small, tucked away. Transparency is common in the midwater, among jellyfish, salps, larvae, and some fish, a quiet invisibility that helps them survive. The deep ocean is cold, but there are warm pockets, places where heat escapes from the Earth's interior. Hydrothermal vents, as mentioned, release water heated to hundreds of degrees Celsius, creating localized warm zones in the otherwise freezing deep. These warm areas support unique ecosystems, but they also create challenges. The temperature gradient near a vent can be extreme, with water temperature dropping from boiling to near freezing over just a few meters. Animals living near vents must tolerate rapid temperature changes or position themselves carefully to avoid the hottest water. Some vent animals have proteins that are stable at high temperatures, while others rely on behavioral adaptations, moving in and out of the warm water as needed. Not all deep-sea animals are small. While many are tiny, adapted to conserve energy in a food-poor environment, some are enormous. Giant squid, colossal squid, giant isopods, giant amphipods, Japanese spider crabs, all reach sizes that seem impossible for their relatives in shallow water. Oarfish, the longest bony fish in the world, can reach lengths of over 10 meters, with long ribbon-like bodies and a mane of red fins. They live in the midwater, drifting vertically through the water column, feeding on plankton and small fish. Oarfish are rarely seen alive, and they may have inspired legends of sea serpents, their long, undulating bodies glimpsed at the surface before disappearing back into the deep. Deep-sea sharks are often slow-moving and sluggish, adapted to conserve energy. The Greenland shark, mentioned earlier, is one example, but there are others. The frilled shark, with its eel-like body and rows of needle-sharp teeth, moves slowly through the midwater, hunting for squid. The goblin shark, with its elongated snout and protrusible jaws, is a deep-sea scavenger and predator, rarely seen but occasionally caught in fishing nets. These sharks are ancient-looking, with features that have changed little over millions of years. They are survivors, adapted to a stable, unchanging environment, and they remind us that the deep ocean is a refuge for life that has persisted since ancient times. The deep ocean is not entirely isolated from the surface. Currents, both horizontal and vertical, connect the surface and the deep, transporting water, heat, nutrients, and even animals. Vertical mixing, driven by winds, tides, and density differences, brings deep water to the surface and surface water to the deep. This mixing is essential for ocean health, redistributing oxygen and nutrients throughout the water column. Without it, the deep ocean would become anoxic, starved of oxygen, and most life would disappear. The ocean is a connected system, and what happens at the surface affects the deep, just as the deep influences the surface. Some deep-sea animals migrate vertically every day, a journey called DL vertical migration. They spend the day in the deep, where it is dark and safe from predators, and rise to the surface at night to feed on plankton, which are more abundant in the sunlit zone. This migration involves millions of tons of animals, moving hundreds of meters up and down every day, one of the largest movements of biomass on the planet. It connects the surface and the deep, transferring energy downward as migrating animals defecate or die and sink, and bringing nutrients upward as they excrete waste while feeding at the surface. It is a daily pulse, a rhythm that ties the ocean together from top to bottom. Deep-sea animals have evolved remarkable sensory adaptations. In the absence of light, other senses become more important. Many deep-sea fish have highly developed senses of smell and taste, using chemical cues to find food, mates, or habitat. Some fish have elongated fins or barbels that they use to sense vibrations in the water, detecting the movement of prey or predators from a distance. Others have electroreceptors, specialized organs that detect the faint electrical fields generated by living creatures. These sensors allow deep-sea animals to navigate, hunt, and communicate in a world where vision is limited or useless. The deep ocean floor is not flat. It has topography, texture, and variation. There are abyssal hills, small ridges rising a few hundred meters above the surrounding plain, formed by volcanic activity at mid-ocean ridges and then carried away by seafloor spreading. These hills cover much of the deep ocean floor, creating a rough, uneven surface. There are also seamounts, trenches, ridges, plateaus, and canyons, each with its own geology and ecology. The seafloor is a landscape, as varied as any on land, though most of it has never been mapped in detail. We know the surface of Mars better than we know the floor of our own ocean. Manganese nodules are potato-sized lumps of metal-rich rock that litter parts of the deep sea floor. They form slowly, over millions of years, as dissolved metals in seawater precipitate around a nucleus, building up layer by layer. These nodules are rich in manganese, nickel, copper, and cobalt, and they have attracted interest from mining companies. But the deep sea floor is not empty. It is home to countless species, many of which live on or around the nodules. Disturbing the seafloor to extract nodules could destroy these ecosystems, and because deep-sea life grows slowly and reproduces infrequently, recovery could take centuries or never occur at all. The deep ocean is remote, but it is not immune to human activity. Deep-sea mining is a contentious issue. The metals in manganese nodules and other deep-sea deposits are valuable, used in electronics, batteries, and other technologies. As demand for these metals grows, so does interest in deep-sea mining. But the environmental impact is uncertain. Mining would disturb sediment, creating plumes that could smother animals and disrupt feeding. It would remove habitat, destroy nodules that took millions of years to form. It would produce noise and light in a quiet, dark environment. Scientists are still studying deep-sea ecosystems, trying to understand their complexity and resilience, but mining operations are already being planned. The deep ocean is on the edge of a new industrial frontier, and the consequences are unknown. Plastic pollution has reached the deep ocean. Microplastics, tiny fragments of degraded plastic, have been found in sediment samples from the deepest trenches, in the stomachs of deep-sea fish, and in the tissues of animals that never come near the surface. Plastic debris, bags, bottles, fishing gear sinks slowly from the surface, drifting down through the water column and settling on the sea floor. Some deep-sea animals ingest plastic, mistaking it for food, and it can block their digestive systems or release toxins. Plastic pollution is a surface problem, caused by human activity on land and at sea, but it does not stay at the surface. It spreads, carried by currents and gravity, contaminating even the most remote parts of the ocean. The deep ocean absorbs noise from human activity, and this noise is increasing. Ships, sonar, seismic surveys, drilling all produce sound that travels through the water, sometimes for thousands of kilometers. This noise can interfere with the communication, navigation, and hunting of marine animals, particularly whales and other cetaceans which rely on sound. Some deep-sea animals may also be affected, though less is known about them. The deep ocean, once a place of near silence, is becoming noisier, and the long-term effects of this noise pollution are not yet understood. It is one more way humans are changing the ocean, often without realizing it. Climate change is affecting the deep ocean, though the effects are slower and less obvious than at the surface. The deep ocean is warming, very slowly, as heat absorbed by the surface is mixed downward by currents. This warming can affect deep-sea animals, which are adapted to stable, cold temperatures, and it can destabilize methane hydrates, releasing methane into the water and atmosphere. The deep ocean is also absorbing carbon dioxide, which lowers the pH of seawater, a process called ocean acidification. Acidification affects the ability of animals to build shells and skeletons, and it may disrupt entire ecosystems. The deep ocean is not isolated from climate change. It is part of the Earth's climate system, and it is responding to the changes we are causing. Deep-sea animals are difficult to study. They live in an environment that is hostile to humans, and bringing them to the surface often kills them or damages them beyond recognition. Changes in pressure, temperature, and light are traumatic, and many deep-sea animals do not survive collection. Even those that do often look and behave very differently at the surface than they do in the deep. Scientists have developed new methods to study deep-sea life in situ, using remotely operated vehicles, autonomous underwater vehicles, and specialized submersibles. These tools allow scientists to observe animals in their natural habitat, to measure environmental conditions, and to collect samples carefully. But deep-sea research is expensive, time-consuming, and limited. Most of the deep ocean remains unvisited, unstudied, unknown. Bioluminescent bacteria are often symbiotic, living inside the light organs of deep-sea animals. The bacteria produce light through a chemical reaction, and the host provides them with nutrients and a safe environment. This relationship benefits both partners. The bacteria have a stable home and food source, and the host has a controllable source of light, which it can use for hunting, camouflage, or communication. Some animals acquire their bacteria from the environment, filtering them from seawater and cultivating them in specialized organs. Others inherit their bacteria from their parents, passing the symbionts from generation to generation. Bioluminescence in the deep sea is often a collaboration, a partnership between host and microbe. Some deep-sea animals produce light without bacteria, using their own cells and biochemistry. This is called intrinsic bioluminescence, and it involves specialized cells called photocytes, which contain the chemicals luciferin and luciferase. When these chemicals react, they produce light. Intrinsic bioluminescence gives the animal more control over its light production, allowing it to flash or glow on demand without depending on bacterial symbionts. However, it also requires the animal to produce and store the chemicals itself, which can be energetically costly. Different species have evolved different solutions, some relying on bacteria, others on their own biochemistry, and still others using a combination of both. The deep ocean is home to many species of octopus, and they are diverse in size, shape, and behavior. Some are small, no larger than a fist, while others are as large as a person. Dumbo octopuses, named for their ear-like fins, drift through the water using these fins to propel themselves, feeding on worms and crustaceans on the seafloor. Other deep-sea octopuses are more sedentary, hiding in crevices or on the sediment, waiting for prey to come within reach. Octopuses are intelligent, curious animals, even in the deep sea, and they have complex behaviors using camouflage, ink clouds, and jet propulsion to escape predators. They are solitary for the most part, coming together only to mate, and they often die shortly after reproducing, their lives brief but intense. Fossil remains in deep-sea sediment tell the story of Earth's climate history. Layers of sediment accumulate slowly on the seafloor, building up over millions of years, and within these layers are the shells of tiny plankton, particles of dust, and chemical traces of past conditions. By drilling cores into the sediment and analyzing them, scientists can reconstruct past temperatures, ocean currents, ice ages, and atmospheric composition. The deep ocean is an archive, preserving records that go back hundreds of millions of years, far longer than any record on land. It is a library of Earth's history, written in mud and shells, waiting to be read. Some deep-sea animals are living fossils, species that have changed little over millions of years. The coelacanth, a large fish thought to have gone extinct with the dinosaurs, was rediscovered in the 20th century, alive and well, living in deep water off the coast of Africa and Indonesia. Horseshoe crabs, though more common in shallow water, have deep-sea relatives that have existed for hundreds of millions of years, virtually unchanged. Nautiluses, with their spiral shells and simple eyes, are relics of a time when their relatives, ammonites, filled the oceans. These living fossils are reminders that the deep ocean is a stable environment where evolution proceeds slowly and ancient forms can persist. Deep-sea sponges are among the simplest animals, lacking organs, nervous systems, or even true tissues. But they are remarkably successful. They filter water through their porous bodies, extracting bacteria and organic particles, and they can live for thousands of years. Some deep-sea sponges form vast gardens, covering the seafloor and providing habitat for countless other species. They are sessile, rooted in place, but they are not passive. They actively pump water, sometimes filtering their entire body volume every few seconds, and they defend themselves chemically, producing toxins that deter predators. Sponges are ancient, among the first multicellular animals to evolve, and they thrive in the deep sea, quiet and persistent. Sea pens are colonial animals related to corals and sea anemones. They anchor themselves in soft sediment and extend feathery branches into the water, capturing plankton with tiny polyps. They are named for their resemblance to old-fashioned quill pens, and they are often bioluminescent, glowing when disturbed, a defense mechanism that may startle predators or attract larger predators to eat the disturber. Sea pens are common on the deep sea floor, especially in areas with soft sediment and gentle currents. They sway slowly in the water, like fields of underwater grass, and they provide structure and habitat in an otherwise flat, featureless environment. Brittle stars are relatives of starfish, but they have long, thin arms that they use to crawl across the sea floor or to capture food. They are incredibly abundant in some parts of the deep sea, sometimes covering the sea floor in dense mats. Brittle stars are scavengers and filter feeders, eating detritus, plankton, and small animals. They move quickly for deep-sea animals, using their flexible arms to pull themselves over rocks and sediment. Some species are bioluminescent, flashing brightly when disturbed, a defense that may confuse predators. Brittle stars are fragile, their arms easily broken, but they can regenerate lost limbs, regrowing them over time. Sea cucumbers are soft, sausage-shaped animals that crawl slowly across the deep sea floor, moving with a patient kind of determination, as if time itself has thickened into something you can push through. They feed by swallowing the sediment beneath them, taking in mud and silt and tiny fragments of organic matter, then extracting whatever nutrients they can before releasing the cleaned sediment behind them. It sounds simple, almost humble, but in the deep ocean, it is essential work. Sea cucumbers recycle the seafloor the way earthworms recycle soil on land, turning over the mud, aerating it, redistributing nutrients. In some places, they are among the most common large animals on the abyssal plain, quietly shaping the ecosystem with every slow mouthful of sediment. Some sea cucumbers have evolved stranger methods of living in the deep. There are swimming sea cucumbers that lift off the bottom and drift through the water like pale balloons, using frilled edges or fin-like structures to pulse gently forward. Others have transparent bodies that reveal their internal organs as faint shadows, and some can eject sticky threads or even parts of their own internal anatomy when threatened, distracting predators long enough to escape. Over time, they can regrow what they lose. It is a strange kind of sacrifice, but in the deep sea, survival often depends on the ability to give something up and keep going anyway. All of these creatures, from sponges and sea pens to brittle stars and sea cucumbers, are part of something the deep ocean does very well. It holds on to time. The deep sea changes slowly, its temperature is stable, its seasons are subtle, its storms are distant, and because of that, many deep sea ecosystems have rhythms that unfold on timescales we struggle to imagine. A coral may take centuries to become a reef. A sponge garden may build itself over thousands of years. A manganese nodule may take millions. The deep ocean is not in a hurry, and in a world that often feels fast and loud, there is something calming about that. A reminder that not everything has to rush to be real. But the deep ocean is not only an archive of the past, it is also a living present, and it is connected to us in ways that are easy to forget. The oxygen many surface waters rely on is redistributed by deep circulation. The carbon dioxide we release does not simply vanish. Some of it dissolves into the sea, and some of that is carried downward, stored in deep water for centuries. The deep sea is part of Earth's breathing, part of its long, slow exchange between air and water, between life and chemistry, between now and later. When scientists lower instruments into the ocean, when they send submersibles down into darkness, they are not only exploring a distant world, they are listening to the planet's deeper processes. They are reading the quiet handwriting of sediments. They are watching ecosystems that do not depend on sunlight at all. And sometimes what they find reshapes what we thought life needed in order to exist. It is one reason the deep ocean is so important beyond curiosity. If life can thrive in darkness, in pressure, in chemical-rich water near vents, then life might also thrive in places like Europa or Enceladus, moons with hidden oceans beneath ice. The deep sea becomes a mirror, reflecting not only Earth's past, but possibilities elsewhere. And still, for all its mystery, the deep ocean is not separate from us. It receives what we drop. It absorbs what we release. It carries the echoes of our ships. It holds our heat. And it does all of this quietly, without complaint, without spectacle, just as it has held the slow motions of the Earth for millions of years. Tonight, as you listen, you don't need to solve the ocean. You don't need to hold every fact in your mind. You only need to let the idea of it wash through you gently. A vast, dark world beneath the surface. A place of slow snow, of glowing creatures, of ancient corals and silent plains. A place where time rests heavy and steady, and where life somehow continues. And as we move toward the end of this journey, we can begin to rise, not quickly, not abruptly, but with the same softness we used to descend, because even the deepest places are still part of the same ocean, and the ocean in the end is one continuous body of water, one long, slow movement around the planet. Imagine now that you are drifting upward very slowly, as if the water itself is lifting you. In the deep, there is no sudden change. There is only gradual transition. Pressure eases a little. The cold remains, but it feels less absolute. The darkness is still thick, but every now and then a faint spark passes in the distance. Some tiny animal flashing a signal, a private language of light that lasts only a second and then returns to silence. The deep sea does not feel empty when you think about it this way. It feels spacious, like a huge quiet room where life moves gently, without hurry. Creatures drift instead of rush, predators wait instead of chase. Everything seems designed to conserve energy, to use only what is needed, to be efficient and calm. There is something almost meditative about that kind of existence. A reminder that stillness can be a strategy, that slowness can be strength. As you rise toward the twilight zone again, you can picture the daily migration, millions of small bodies moving upward at night and sinking down again by day. A pulse, a breathing motion in the ocean itself. Lanternfish in vast schools, hatchetfish like thin shadows, jellyfish glowing softly like drifting lanterns. Even without sunlight, the ocean has rhythms. Not the loud rhythms of land, but quieter ones, like the slow turning of pages. And above that, higher still, you come toward the boundary where sunlight begins to matter again. The edge of the deep. The place where the last faint blues dissolve into true light. It's strange to think that so much of the planet exists beyond that boundary, an enormous living world hidden beneath a thin layer of brightness. If there is one thought to carry from this journey, it might be this. The deep ocean is not distant in the way we imagine. It is beneath us, connected to every shore, every cloud, every breath. It holds carbon, it stores heat, it shapes weather, it supports fisheries. It contains stories written in mud and shells and ancient bones. It is both unknown and essential at the same time. And maybe that is part of why thinking about it feels so calming, because it reminds us that the world is larger than our worries, larger than our schedules, larger than the noise of the day. Somewhere, right now, far below the waves, a sea cucumber is tracing a slow path across the sediment. A coral is growing by fractions of a millimeter. A sponge is filtering water through glass-like lattices. A tube worm is waving its red plume beside a vent, living on the chemistry of the earth. All of it happening without urgency, without audience, without needing to be seen. Now, let your mind loosen its grip on details. You don't have to remember the numbers. You don't have to hold on to the names of zones or creatures. You can let them drift away like marine snow sinking slowly into the soft seafloor of sleep. If your thoughts wander, let them wander. If your breathing has slowed, let it stay slow. If your body feels heavier, let it be heavy. You've traveled far tonight, down into the largest habitat on Earth, into a place where light becomes rare and life becomes strange and beautiful in quiet ways. And now you can rest. Thank you for spending this time with Sleepy Lab. If this gentle descent helped you relax, you can always return whenever you need a quieter ending to your day. For now, let the ocean fade into the background of your mind. Let the darkness become soft. Let the silence become warm.